Okay, so good morning. Welcome to the second lecture on tools for string phenomenology. So yesterday, this was again the overview. Yesterday we sort of spent some time doing more sort of a philosophical discussion about how we should be approaching string model building, or what would be a systematic avenue for doing that. That was sort of how we got to bottom-up model building. Then how we discussed gauge degrees of freedom localized on branes as sort of a nice framework where we can start with something where we can, first of all, ignore any kind of string theoretic issues and just study, in fact, these so-called local models, which are half-twisted Super-Yang-Mills on some curved surface S, which was, for our purposes, a four-dimensional surface, four real-dimensional surface, a Kähler surface actually, times R3,1. And so the working example, which for obvious reasons I'm picking, is that we're looking at an 8-dimensional Super-Yang-Mills on a complex surface, which is really the local limit of what we'll later on get to, in fact today, being local F-theorem models. And what we discussed is sort of how to calculate, once you have sort of a theory like this, say zero modes of these twisted fields. So this had to be twisted along the surface S, this theory, to be well defined. So you had scalar supercharges. We sort of had some rules how we actually count the zero modes in the background of some gauge field that switched on, say in a U1 direction. So some gauge group G that we sort of break down with this flux, which is modeled on the surface by a line bundle. And then we have to compute these cohomology groups, where the powers of the line bundles are determined by the U1 charges. Okay, so this is sort of the zeroth order thing that you can do in these kinds of setups. Usually, however, when we look at branes and try to model the MSSM or gut theory to engineer actual matter, Dieter, do you have a question? We usually look at intersections of branes, and that's really also going to be the source of matter in this context. So what I'll discuss, so this was the last bit that we sort of didn't get to yesterday, is on S, we're sort of thinking of this is like a brane mapping times the transverse R3,1. There's really the way to get localized matter on these kinds of surfaces is actually to look at another brane that intersects that surface over, say, a complex curve from the point of view of the 8D Super-Yang-Mills that corresponds to looking at a 6-dimensional defect theory that lives on R3,1 times that curve sigma. Okay? So that's one way of looking at it. The point of view that will be sort of crucial for today is I would like to think of that in terms of Higgsing a higher rank gauge group down to the gauge group that we're actually interested in, and this gives rise to bifundamental matter and, in fact, chiral matter in the long run. Okay, so this is like the picture that you should have in mind. So I'd like to think of matter as being generated from looking at a higher rank group. For example, if you'd like to engineer an SU5 model, we start with SU6, right? That's sort of one of the ways you can go one rank up. Then I can think of sort of a stack of branes, really like in this sort of intersecting brane picture. As a stack of branes, open strings ending on it. The gauge degrees of freedom are in the 35, the adjoint of SU6. And I can think of sort of generating matter for the SU5 by switching on an adjoint Higgs scalar field VEF that breaks it to an SU5 times U1. The 35 will decompose into the adjoint of the SU5, the adjoint, quote unquote, of the U1, and then two other multiplieds, a 5 and a 5 bar. Right? And the 5 and the 5 bar are precisely bifundamentals between the SU5 and the U1. So in this way, when I sort of think of this picture of, I have a stack of branes, then I tilt one of these branes off at the intersection of this single brane with the actual initial stack. I have these localized string modes, and these are precisely going to give rise to these bifundamentals. Right? So the picture is sort of, I think, clear. This is something that you've seen before, but the way I'd like to think about it is in terms of really, we're thinking of this as switching on a VEF for an adjoint scalar field that generates sort of a mass, in fact, for these 5 and 5 bars. And this sort of, intersection, which in our case will be a complex codimension 1 subspace, is characterized by the vanishing of this VEF, phi, that we've switched on to break this higher rank gauge group. Okay, and something similar, of course, we can do in the case of SU5, not going to SU6, but SO10, and in that way we'll actually generate then the remaining matter that we're looking for. Here we had 5 and 5 bar. For the SO10, we get the 10s. Okay? So this gives us bifundamental matter. The really interesting thing is, of course, how do we actually get chiral matter, right? And so the story is very similar to the discussion we did yesterday. We switch on some line bundles. We restrict them to, in this case, the curves, and have to count the 0 modes of these, twisted fermion fields that we discussed in this restricted theory. So, for example, if I have a U1 bundle on, say, this sort of stack of branes here, and then on this stack of branes here, called L1 and L2, and that breaks sort of the, here it is a more general case where this could also be some non-abelian group, and this one too, that will Higgs this here down to an H1, H2 times 2 U1 factors, right? In the picture, G2 is trivial, H2 is trivial, and G1 is 0, so we just get a G1 goes to H1 times a U1, but this whole thing will work more generally, right? So you have two representations that are here the adjoint and here the adjoint, and they'll be, decomposed under this remainder group with U1 charges under these two U1s, which are labeled alpha and beta, right? So this is like, could be a 5 and a 10, etc. So how do we count the 0 modes? Again, we have two line bundles that do sort of this, that are, in these U1 and U1 2 directions. And so the 0 mode counting is a cohomology. You have to count H0 on this intersection curve sigma of k sigma to a half. This is sort of like this twisting bundle that we have also in the other case, times the U1 bundle for one U1 to the charge alpha of the state that you're counting times L2 to the charge of the second U1, right? And so this all restricted to sigma will give you some bundle. You have to count the sections essentially of that bundle. Okay, so how do we actually do this? Again, let's go back to sort of the most simplest kind of example that we can anticipate. Yesterday we discussed P2 for the surfaces. Here, of course, the simplest kind of curve is a P1. That's just sort of one dimension down. The example, the line bundles in this case are just classified by their degree n, so I'll always call them O of n, and here the way you should think about this is those have transition functions that are like z to the n. And the sections are such that if O of n and n is positive or equal to 0, then it has n plus 1 sections. And what are these sections? They're actually all the polynomials from degree 0 up until degree n. And if it's negative, then you don't have any holomorphic sections, right? So because you'd get, powers of z in the denominator. Okay, so this is sort of the simple kind of setup now we can apply to this chirality counting on some matter curves. Cool. All right, so there's another sort of little piece of information that we need, which is this k sigma to the half that appeared for the P1. We said yesterday for the PNs, there's only really one class, which is the hyperplane class, and the canonical bundle is given by minus n plus 1 times the canonical class. So here, this means we have kp1 is actually minus 2h, so this is a degree minus 2 bundle. If we just look at sort of, what this translates to, using this Serre duality, this H0 of P1 of O minus 2 minus n, which is really H1 of P1 of On, is minus n minus 1, just from up here, right? So that's a little sort of fact. All we need really is that Kp1 here is O minus 2, which will enter into the chirality formula in this way here. So K sigma to the half in this case would just be O of minus 1. Cool. So let's look at the actual example that we're interested in. Say we have, our guts group is SU5, sigma is a P1. So for example, right, so that group could be an SU5 living on a DPN surface, and one of these P1s is like one of these exceptional classes that we had from the blowups of the DPN. And we'd like to generate 3 generations of 5-bar matter and 3 generations of 10 matter, right? So this is something that we would like to do in order to at least have sort of bare bones of a gut model. So SU6, we said, we can decompose the adjoint to the 5-bar, and the charges under this U1 were +6 and -6. And similarly for the SO10, right, so now we're starting with a stack where locally, in this higher, once you, switch off the Higgs valve, you have an SO10 gauge group. That's Higgs down, and you get in the decomposition a 10 and a 10 bar with the charges +4 and -4 for the U1. Okay, so this is, I know, just doing the group theory yourself or looking it up in landscape, it becomes more complicated. Then now the question is, how do we actually count these, how do we get, say, non-trivial, offset of these versus these ones here? So we said that, the counting goes as H0 of P1 on the surface. This is the, spin bundle contribution tensor with the line bundle to the power of the U1 charge. So this cohomology group here will count the number of 5s, and this one will count the number of 5 bars. And what we'd like to have is that this is 0 and this is 3, right? So that's sort of where at least the difference is equal to 3. In this case here, to engineer that, right, we said for Pn, remember, for P1, the degree n bundle has n+1 sections. So here, we can get this to be 3 if this restriction here is actually an O of 3 bundle, right? Because O of 3 tensored with the O of -1 gives us an O2, so it has 2 + 1 is 3 sections. And sure. So this is, well, I mean, so basically, right, you have a line bundle here that is precisely engineered so that it counts the 0 modes corresponding to, so that it actually couples to the fermions in the way that, this U1 charge is, that U1 is actually normalized. Yeah, so you really, this L bundle is in the U1 direction here. Yes? That's the embedding of these 2 groups into the SU6, right? Yeah, it's a choice. You can also change it. For example, if you, later when we do gut breaking, sure, it will just change what these guys are, right? All you have to do is that it's consistently done, that when you decompose this, that indeed, I think what's important is, first of all, here you have the zeros, and then these are the relative charges. Right? You can still change the normalization of these. Okay, similarly here. Okay, right, so this is how we can, in this very simple setup, have, say, a P1 and already get, it seems like, a 3-generation model. Of course, we haven't really said anything about, how this is now realized in the surface, et cetera, but this is sort of the setup. This will give us, if we choose these kind of degree 3 bundles on the Riemann surface, that will actually give us 3 10s and 3 5 bars. Okay, are there questions about this? This should be completely clear. So this was the matter, and now, of course, the additional information that we also like to get from this framework is that we can get the Yukawa couplings. And again, here, the idea is not to think of it in terms of this sort of intersecting brain picture and now saying all these are intersecting, so there should be a coupling that can be generated here, but actually think of it in terms of, again, a higher rank gauge group. So you're starting with a rank 2 enhancement, so GP is sort of this rank 2 enhanced group that can either be an SU7, SO12, or E6 in the case of SU5. And you break this to SU5 times now 2 U1s, right? So intuitively, the picture is you have a stack of, say, 7 brains, and you peel off one like this, that gives you matter, and you peel it off, another one off like that, and then you get this kind of interaction point here. Yes, but the way I'd like to really think of it is in terms of this Higgs web that does this breaking for you. So for example, if you look at an SU7, again, we start with the adjoint of the SU7. That's Higgs down to now SU5, U1, U1. This is the adjoint content of the remaining gauge group. Then all the other representations are 5 bars or singlets with these U1 charges that are at the bottom here. Okay? And so now you can ask, so what is a consistent, combination of representations of the SU5 that can actually form a coupling here? So if you look at the charges of this 5 bar, and the singlet, indeed, all these charges, the U11 and the U12 charges, add up to 0. So they would actually generate consistent coupling at this point. And similarly, the opposite, the conjugate fields, 5 bar, 5, and 1. Right, so this is a coupling that's not quite one that we really necessarily are required to have. It will couple, say, a 5 and a 5 bar to a singlet field. So this is actually a useful coupling if you, for example, would like to do something, a gauge mediation in this context. So this could be like messenger fields coupling to a singlet, and that's actually how we'll use it tomorrow. The more interesting couplings are the SO12 and the E6, which are actually, coming like a 10 5 bar 5 bar or a 10 10 5 coupling, and they come from really the same process. You look at the adjoint and you ask, what are the allowed sort of couplings that can be generated respecting these U1 charges? So for example, from the SO12, indeed, we get 5 bar 10, right? So this has invariant charges here and here, and the opposite ones here, right? So this gives us the bottom type Yukawa coupling. And then the interesting one is from E6, which is adjoint 78. We sort of Higgs it to the 2411. That can generate now a coupling that's sort of in perturbative type 2b, at least, with compactified and Calabi-Yau with orientifolds had not been sort of constructed here. It's possible to get it from this exceptional gauge group, Higgs to SU5 times U1 times U1, and indeed you get the 10 10 5 coupling here. And just checking the charges, they indeed add up to 0. Okay? So this is sort of just heuristic. It's just group theoretically saying there's a consistent way I can Higgs these great gauge groups and get these kinds of couplings, top and bottom Yukawa coupling. Okay, so this is now the picture. We have a gauge group that's SU5 in our case. Going sort of one rank up, we have the choice of SO10 and SU6. Going 2 ranks up, we have this. If we would like to sort of put all this together into one framework, meaning getting this from one underlying gauge group, you at least have to go to an E7. And in fact, it's very useful sometimes to have additional states that you actually get from an E8. So starting with the E8 and then Higgsing that down all the way to SU5, that should give us a framework where we can get all the data that we need, the Yukawas and the matter. There's a question.
So by using group theory, you can write down some terms in the superpotential.
Sure.
What about the rest? You can add other terms as long as it's gauge invariant?
Sure, so you can write down other terms.
But what about
and you will have to
sign?
forbid these terms. Sorry?
What about the relative sign and relative coefficient? That's to be left unfixed.
Well, you mean the lambda that's in front here?
Yes.
Yes, so I will not be computing this for you in this framework, no. So the Kähler, I have not discussed the Kähler potential at all yet, right? At this moment, all we're discussing is this will generate these kinds of, superpotential couplings, okay? And this isn't even like, at the moment, we've just done group theory, okay? So we have, in fact, not even started talking about superpotentials. I'm saying this will allow us to now, in the way we describe these theories in terms of Higgs bundles, to actually really get superpotential couplings of this kind. Right? Kähler potential is much more difficult in this context, actually.
So it's the model is still far from fixing. You still can have room to add more terms.
Well, so if you want to ask a very precise question, one question you can ask is, first of all, this will, we will get to this. So if you want to get ahead like that, fine, that's okay with me. So we can start with an E8, and we can Higgs it down. You'll get all kinds of things, right? Now the question is, for example, why don't you generate couplings that generate proton decay, things that you do not want to have, like dimension 5 proton decay, dimension 4 proton decay operators. And for that, you need to do more work, and we will discuss this. There'll have to be symmetries in your model that forbid these kinds of couplings. Okay? So this is sort of saying that's how we get the bare bones, the 5s and the 10s, and also the Higgses, if you like. Okay? And we will discuss, now we will go stepwise understanding how this will fit into something that you could, call a phenomenologically sound model. Okay? So we will get lots of couplings that are not desirable, and we will find a mechanism how we forbid them. Okay? Any more questions? Okay, so this is now we get to lecture 2, and the question was, how do we do this, right? So far we just did some group theory, so this is really what we just discussed. As I said, I would like to think of this the generation of matter, not just in terms of, we decompose the adjoint, et cetera, but really in terms of this adjoint scalar VEF. And if we go back to actually our 8-dimensional gauge theory, right? So remember we had these modes, psi alpha and chi alpha, which were these twisted fermion fields. So if you look at the equations of motion for these fields, the way they look like is, so this is this psi alpha, that's the, one of these left chiral fields that we have there. This phi, if I now switch on some VEV in some adjoint direction for the SU6, this really acts like a type of mass term for these fermion fields. And likewise, this phi here for this d chi. So in a way, this is, consistent with this picture that we had before, that switching on a VEV, say in a U1 direction, a higher rank gauge group, will, first of all, break all will generate us the adjoints for the remaining gauge group, but also for the remaining fields, these psi and chi's will give us sort of masses. The masses will vanish at the locus when the VEF of the phi field is actually 0, and that's precisely the codimension 1 locus, this matter curve, where these fields are localized on massless fermions. Okay, so this picture of really not thinking in terms of intersecting branes and flipping them around, but really in terms of these Higgs fields, this will be sort of now the guiding principle in this lecture. Similarly here, this will now be switching on an adjoint Higgs field in 2 U1 directions to get the Yukawa couplings. And in fact, to get to this picture with all the full E8, we end up with this here, right? So this is something that we saw already in, at the very beginning yesterday in the heterotic context. But here it came about by asking, we would like to have, for an SU5 model, both the matter and the Yukawa couplings all coming from some higher rank gauge group that we can then Higgs down. So we started with an E8. And so this is sort of the E8 Incan diagram, of course. There's an SU5, so these roots there are the, labeling the SU5 gut. Then the commutant of that is an SU5 perp. These are the red nodes. And Higgsing this from SU5 to these two, from E8 to these two SU5s, we get all this adjoint stuff, right? So in fact, these will be the gauge fields for the gut group, and all these representations for, the SU5 groups. So the way I'd like to think of this whole process, which will end up giving us, if you always look at the second entry, which is the representation content of the SU5 gut group, right here, this is the adjoint. This will give us 5s, this 10 bars, 5 bars, and 10s. Then really this whole process is described by switching on now in the SU5 perp direction, adjoint VEFs, phi, right? So this is sort of the slightly more general version of what we discussed for the matter from SU6. So this phi field will play the role of how we now get from the E8 down to an SU5 gut. Okay, so the interesting thing is now if you now really label this in terms of these representations, the blue stuff is really what you should be looking for. That's, counting the different types of gut representations. So if you look at, for example, the 10, right, the 10 is labeled here by the fundamental of the SU5 perp. So in fact, the fundamental weights here give us sort of a way to label all the possible 10 representation we get for the SU5. So if you, for example, look at this phi field in the SU5 perp directions, and we assume that that actually is a diagonalizable Higgs field with eigenvalues lambda 1 up to lambda 5, with the sum, of course, being 0, so that we have an SU5 Higgs field, then this can be thought of giving mass to all these, like in the case of the SU6, the mass of all these fields of the fermions is set by this F, and the zero modes localized at the vanishing locus of this Higgs field, right? So for example, for the 5 and 10s, I said that the 10s for the SU5 dot are labeled by the fundamental of the SU5 perp. So that's actually precisely localized at the vanishing of the fundamental weights lambda, these eigenvalues here, of the SU5 perp. For the 5 bars in the gut group, which appear here, these are labeled by the 10 of the SU5 perp. So these are, right, the 10 is just the antisymmetric, so these are labeled by the vanishing of lambda I plus lambda j. So in this way, we can read off from this decomposition saying, this is came about by switching of this phi field, having a F for that, diagonalizing it. This is precisely now giving us a means of describing the loci where these fields are actually located, right? And they're labeled by either these lambda I vanishing or lambda I plus lambda j vanishing. Okay, so this is sort of, just looking at this decomposition. The really sort of powerful machinery behind this whole thing is looking at the so-called Higgs bundle and mapping that to an actual geometric object in this theory. So we said we have this Higgs field in the SU5 perp that breaks the A to an SU5. So, so far we just looked at the eigenvalues lambda 1 up to lambda 5. But really, we can look at this sort of characteristic polynomial, right? Determinant of S minus this matrix. That'll be a polynomial in S, right? It'll be a fifth order polynomial with some coefficients be, in this way. There's no B1 term here as to the 4 because B1 is just the sum of all the eigenvalues that vanishes for an SU5. And so now we can ask, the zeros of this give us the eigenvalues lambda. So this characterizes really the possibilities for this Higgs field in the SU5 perp direction. This little comment here will become clearer later. So if you want to ignore it for the moment, that's totally fine. So this S actually will be a section of the canonical bundle of the surface. But that's just if you like this kind of stuff. Anyway, so just looking at this here, doing linear algebra sort of 101, right, we just read off that these BM coefficients are just really like the traces of phi to the m times some B0, which appears here. Or writing out really what this means, characteristic polynomial, B5 will be just a product of all the lambdas. B4 is sort of the symmetric, fourth order polynomial, etc. And again, the sum of all the lambdas is 0. So all these coefficients, right, turn out to be symmetric polynomials in the eigenvalues of this matrix, phi. Now, if you look at this sort of equation, right, which is now, this is really, I would like to think of this as some defining equation. This is sort of some, bundle that lives over the surface S. If I look at this equation, I can ask, so we had this, initial insight that all the matter would be localized where the eigenvalues lambda I vanish or lambda I plus lambda j vanish. So where do I see this in terms of this surface S, which is surface C, which is the so-called spectral cover for this Higgs bundle? Well, B5, if you go back, so B5 is just a product of all these lambdas. When that vanishes, that means all these eigenvalues lambda I, one of these eigenvalues lambda I will vanish. So that's precisely what we said is the 10 matter. Right? Do you remember? So this is here, the 10 localized at lambda I equals to 0 because the 10s are labeled by the fundamental weights of the SU5 perp. Right? And so now we're not just setting all the lambda I to 0, but actually there'll be this combination, which is called B5, appearing in this characteristic polynomial here. So B5 is equal to 0 tells us that's the matter locus for the 10. Likewise, we can ask, so what's the combination lambda I plus lambda j that was giving us the 10 representation of the SU5 perp that was, giving the multiplicities for the 5 bar of the SU5 gut. So the lambda I plus lambda j, this here can be rewritten in terms of these coefficients b in this way, b0, b5 squared, etc. So this will be always called p is equal to 0. So this combination vanishing. So that's again some condition. If you go in sort of this equation to the locus where p is equal to 0, then that's precisely the locus for the 5 bar matter. And so now the Yukawa couplings, right? So if we think of, for example, the bottom Yukawa coupling, the bottom Yukawa coupling is 5 bar 5 bar 10. So that's when you have a vanishing of 2 of these 5 bar representations and 1 of the 10 representations, right? So that's precisely when this kind of thing holds. And looking at what that translates into these, symmetric polynomials, that's just B3 is B5 is equal to 0. And likewise, E6, it gave the top Yukawa coupling, and that sort of E6 locus is when, the 10, another 10, and the 5, all the charges add up to 0, right? This is, when I translate it back into terms of these B's, is B5 is B4 is equal to 0. And finally, if I set all these coefficients except for B0 equals to 0, I sort of get like a whole E8 structure. Anyway, this is sort of just as an aside, but this is now a way we've translated our insights from just this group theoretic decomposition, we Higgs the E8 down to the SU5 perp times SU5 gut, into a condition on this equation, which is this spectral cover equation. Right. So the way I would like to think of this spectral cover is really in terms of, it's not just an equation that's the characteristic polynomial of this Higgs field, but really it is something that is a 5-fold cover of this S gut. And why is this sort of a good picture? Well, if we go back to here, right? So here we said this is really coming from a Higgs field that lives over this gut surface. It varies over the gut surface, and at certain loci, when these lambda vanish, it gives rise to matter and Yukawa couplings. So in this way, now the surface C, right, which is now a 5th order surface, can be thought of like a 5th order covering where each of these sheets is labeled by one of the eigenvalues of it, right, over the surface S gut. And that's why I was saying S is really a section of the canonical bundle of this surface. Okay, and so the Higgs fields usually doesn't break it to just SU5 gut, but generically will break it all the way to SU5 gut times SU5 perp or U1 to the 4, depending on the precise structure of the Higgs field. So we'll discuss what the structure of this spectral cover is. This picture, for example, would actually give you just an SU5 gut and nothing else, right? Because all these eigenvalues are actually sort of connected to each other. Anyway, so the point is this cover is a 5-fold covering where, however, the coefficients are not just these eigenvalues lambda I of the Higgs field, but they're actually these symmetric polynomials, right? So if I actually would like to know what each one of these lambda i's corresponds in terms of these Bn, that requires me to invert this equation, or put differently, right, this is a branch covering. If each one of these sheets is one of these eigenvalues, it's a branch covering over S gut, where the branching is precisely sort of encoded in the spectral equation. Okay. So usually the branching is such that all of these lambda i's are connected to each other. Now, if you refine the choice of these coefficients B, such that, for example, this cover actually factors, then you have a possibility that this actually has sort of disconnected components, or in terms of looking at this branch cover over S gut, we can say there's a monodromy group that acts on as a permutation group on these weights. And if this is like the whole permutation group S5, it will connect all the sheets, then we don't get anything but an SU5. If there is sort of reduced monodromy, meaning some subgroup that's inside S5 that acts sort of transitively, then actually we get that in each of these, it does not act transitively, right? So it actually has some decomposition. So for example, this here would be a Z2 times a Z2 times a trivial factor. It only maps lambda 1 to lambda 2, lambda 3 to lambda 4. Then you have a chance of getting an additional sort of U1 factor in your theory. So you don't just Higgs down to an SU5, but actually an SU5 times U1s that are realized in terms of each one of these sheets. Okay, so the general sort of story is if lambda I is some reducible representation of the monodromy group of this branched covering, then C factors into n components, and you get n minus 1 gauged U1s. N minus 1 because, again, the sum of all these lambdas vanishes, so you get maximally U1 to the 4 additional sort of sets of gauge bosons. Okay, so this is now the full set of coverings that you can consider, labeled by the monodromy groups. So this is the case when each one of them is sort of separate, and that the monodromy group is just the identity. Then you get all 4 U1s. And each one of these other cases is sort of when you have a reduced structure group acting on this covering. So for example, the 4+1 case where you have sort of 4 sheets connected and a single sheet has the option of either you have the subgroup S4 of the S5 permutation group, the dihedral 4, the Z4, or the Klein 4 group. And each one of these will give you a different kind of spectrum in the resulting theory. Another interesting sort of case is this 3+2 splitting, which essentially is S3, so the full S3 permutation group acting on 3 sheets times a Z2 that connects the other 2. Okay. So these ones here are actually really physically distinct, whereas these guys are actually going to be almost the same. There's no difference between these two things, but still you can sort of look at this table of monodromy groups and now look at all the possibilities of, Higgsings from EA to SU5 that is sort of consistently described in terms of this Higgs bundle. Sorry?
There's one subgroup of S5 which is missing in this table,
the alternating group of S5, yeah. No, so that's... Sorry, the what? That? So I don't, so the question is whether you will actually, so we'll see in fact that all these, for example, these two, you will not see a difference in the actual model, right? So we'll have to, we can discuss this actually. I don't think we like all the groups, but okay, that's a good point. We can look, maybe get a new model. So anyway, so what I'd like to do is look at an example to actually make sort of sense of why this is sort of an interesting thing to do, because it really gives you some additional sort of structure in the types of couplings and matter that you'll get. So let's look at this simple example where we just have a Z4, which has one generator at 1, 2, 3, 4, so 1 goes to 2, to 3, to 4, to 1. In the permutation, this is a subgroup of the permutation group, S5. And now we'd like to decompose all the weights lambda I under this C4 group, right? And the sheet sort of connectedness is depicted here. So we have 4 sheets that are connected, and then 1 single sheet labeled by lambda 5. So the fundamental of the SU5 perb then decomposes into sort of the tens that all live up here. That gives us 1 10. And then, right, so there's no way to distinguish these the locus lambda 1 is equal to 0 is connected to lambda 2, lambda 3, lambda 4. And then there's another one that's singled out, that's lambda 5. For the 5 bar, which were labeled by the lambda I plus lambda j of the SU5 perb, there are a couple more options. So we look at the different orbits, and the different orbits are actually either you have to sum lambda 1, lambda 2, and all the images under this action of the Z4, lambda 1 plus lambda 3, or you go between the 2 sheets, between these 2 factors, the fourth order piece and the single order piece, so that's lambda 1 plus lambda 5, plus all the images under the action of the Z4. So this gives us in total 2 possibilities for the 10 that are distinct in this cover, and then 3 possibilities for the 5 bar. Yeah. And so now we can ask, what kinds of couplings are actually consistent? Consistency requires, for example, for the couplings that here all these lambdas add up to 0, wherever the coupling is, either an SO12 or an E6 coupling. So what we get is the 10-1, 10-1, 5-1, that is a consistent coupling. So if we just look at all the sum of these charges, indeed, they're sort of okay, and similarly these. But the coupling, if you look at 10-2, 5 bar 1, 5 bar 2, so that's this one here, coupled to this plus this. If you add up all the charges, indeed, lambda 1 plus lambda 2, lambda 1 plus lambda 5 plus lambda 3 plus lambda 5, that's non-vanishing, and that coupling is forbidden, right? So just by looking at these kinds of, more refined coverings of S-gut, we have sort of certain couplings that are allowed and other couplings that are forbidden. Now you would think normally such a thing is, generated by having additional U1 symmetries, and indeed, factored covers will correspond to having additional U1s, as I said. Here, however, this sort of forbidding this kind of, the 10-2, 5 bar 1, 5 bar 2 coupling, that's actually something you can't just engineer by assigning U1 charges to these fields. So this really comes out from looking at such, a refined monodromy group and then figuring out what kind of couplings are actually consistent with that. So the data that's encoded in the spectral cover and the details of it, is it sort of with a refined monodromy group, or is it all connected, et cetera? That tells us all the possibilities of, first of all, the matter and the Yukawa couplings in these models. Now, we said, in fact, that was sort of one of the questions we had earlier today. You will generate all kinds of different things from your, model that you may not want. Like, for example, this Q cubed L of a lambda coupling that's, a dangerous dimension 5 proton decay operator, and as we discussed yesterday. So one question is, can we actually engineer in our spectral covers which forbid such couplings, right? So this is sort of one question that you can ask. Symmetries were sort of something that's more important, in particular in the context of forbidding such operators. So can we actually build models that forbid the Q cubed L coupling? But differently, I'll call these kinds of things U1 Pechiquin type symmetries, which have the property that the charge of H up and H down don't add up to 0. So now you'll ask, okay, what does this have to do with the Q cubed L operator? If you look at, all your Yukawa couplings, which are 10, 10, 5, and 5 bar 5 bar 10, the Higgses will couple to all these fields. Then the charge assignment, if this is non-zero, then this will be also forbidden by consistency with the standard 10, 10, 5, and 5 bar 5 bar 5, 10 couplings, right? So the Yukawa couplings plus this here will actually be equivalent to saying this coupling is actually not there. So one question is, how do we generate models in the spectral cover context that actually, give us no proton decay Q cubed L operator? And that's sort of this example, 3 plus 2. So, these 4 plus 1 actually models, they have a problem with this. They're not so suitable for that. But you can see, right, so with this list of monodromy groups, you can go down and really study all the possibilities that you can get from this kind of a mechanism. You can study what kind of spectra you get, what kind of couplings you have, and sort of, in fact, formulate under condition so-and-so, you will get a no-go theorem that you can't have, in the 4 plus 1 factored model, a UNPQ realized. So in this 3 plus 2 factorization, which is a 3-sheeted and a 2-sheeted sort of covering, the way the spectral cover will sort of be refined is indeed it will be a cubic polynomial times a quadratic polynomial, which then give a refined version of the standard 5th fold spectral cover for this Higgs bundle, right? So the B5, B4, etc., which were appearing in the standard spectral cover, are now refined so that it has the structure that only a cubic piece sort of has a non-trivial monodromy acting on it here and a quadratic piece. So just multiplying this out, then we get what are the original sort of coefficients Bn in the spectral cover. One condition, which was B1 is equal to 0, which came from the tracelessness, is A1, E0, A0, E1. That's just sort of coming out from this expansion. So we need to solve this equation, for example, by setting a specific choice for these things. So in any case, this will then describe a model with a group S3 times C2. Now we can ask, again, like before, what kind of matter content can we get? So there'll be 2 10 representations, which will come from either this cubic piece or the quadratic piece, and I'll label them by lambda I and lambda a's, which sit either in the first or the second factor. These E1 charges I'll get to in a second. There'll be 2 types of 5-bar fields that will sit either just in the first or in the second piece of the spectral cover, and then there'll be sort of a mixed piece, right? So lambda I plus lambda A will also be a possibility, so there'll be 5-bar fields that are sort of going between these 2 sheets. Okay, so now we can ask, with this sort of set up, what is the different types of couplings that are allowed. The 10-matter curve, right, if you just look at the equations, these were B5 is equal to 0, B5 becomes A3, E2 is equal to 0 from this equation up here, right, from the refined spectral cover. So here, this just says there'll be one component that sits in the cubic piece of the cover and another component that sits in the quadratic piece of the spectral cover. Similarly, for the 5-bar, we said there will actually be 3 components, 5-bar 1, 2, and 1, 2. Indeed, this polynomial p that was p is equal to 0 gave us the 5-bar matter, factors into 3 pieces, which are precisely giving us either a 5-bar here, a 5-bar here, or a 5-bar that goes between. And so now the question is, given this is sort of the labels. This is sort of the different types of matter that we have. These are the weights under the SU5 perp. What type of couplings are now allowed? And the interesting thing is, if I assign sort of the 10 matter to be in the second sheet, right, and then the 5-bar matter up here, then this is the 5-bar Higgs. This is the 5 Higgs actually, and this is the 5-bar Higgs, right? So this one here will be, for example, the 5-bar Higgs. Then this effective sort of, this assignment of the charges under the SU5 perp effectively corresponds to assigning a U1 charge to each of these fields in the following way. So this is really, again, just a normalization. You can just, saying that, for example, here, the 10 can couple. So, for example, you can couple the 5-bar Higgs with the 5-bar. So 1 second, here we go. So we said one condition for a PQ charge to be existent is that the Higgs and the Higgs bar don't have the same, they don't have a U1 charge that adds up to 0. If you look at the 5-bar that comes from the C2 and the 5-bar that comes from going between the 2 sheets, then indeed the sum of these 2 can never add up to 0. So indeed they will carry effectively a non-vanishing sum of a U1 charge. So we can just sort of assign a U1 charge here, then solve for the whole possibilities that we have here. And then the effective U1 charges that you can get out of this are given in this column here. So indeed, the Higgs bar are charged so that the sum of the charges is non-zero. That was sort of one way we defined the PQ symmetry. We can also check that the 10-10-5 coupling and the 5-by-5-by-10 couplings are okay, so the Yukawa couplings are fine, and there will be no Q-cubed-L coupling. Right? So this is just by looking at this refined spectral cover, we obtain an assignment for each one of these representations will carry some weight under the SU5 perp, And effectively, that'll allow us to then read off from all the couplings that we can generate in this framework some U1 charges. Right? So in this case, the refined spectral cover 3 + 2 is equivalent to having an actual U1 symmetry in your problem. Okay? So this is one way you can then start engineering models that have, you know, all the basics of an SU5 gut, plus refined structure like no proton decay. Cool. So this is the, you know, just without addressing chirality, et cetera. What we'll have to discuss sort of in the last 10 minutes or so is how do we now, in this framework of spectral covers, discuss the, you know, actual thing that will give us chirality, meaning fluxes. So I said, you know, the way I'd like to think of this spectral cover is in terms of, you know, a 5-fold covering of the surface S. And really, technically, the proper way to, you know, describe this is the S here, this section here, is actually a section of Ks of the gut surface, right, of the canonical bundle. Or if I go into some, you know, better coordinates, I can actually think of it in terms of embedded in a P1 bundle of Ks plus Os. This is a trivial bundle, that's the Ks bundle. On the P1, I have 2 coordinates. These are the homogeneous coordinates, U and V. And the coordinate that we are using so far is just the ratio U over V. And, you know, U is a section of O1 of the P1, tensor with Ks. UV is the section of O1 of the P1, coming from here. And so the ratio indeed is a section just of Ks. So when you write this here, well, we really have gone into a patch on that P1 and just written in terms of this ratio as is U over V. Okay, so how do we actually formulate in this context, you know, fluxes that we're generating all the nice chirality formulas? So the Higgs bundle data that we discussed so far is really just the spectral data. So C was, just to remember, just the eigenvalue equation for determinant 1 minus the Higgs field in the SU5 perp direction. There's additional data to complete the information that we had from this twisted n = 1 Supergravity theory. There was also a gauge field A that was giving us a vector bundle over the surface S, right? So we had a Higgs field and a gauge field, and so far we've completely neglected this vector bundle part of the story and just focused on the Higgs field. Okay, so how do we actually now construct a vector bundle over S that will encode the data on the gauge field? So this is, again, a very classic and very general construction that one can do. From a spectral cover over a surface, we can construct a vector bundle on the surface S, a UN or SUN vector bundle, by taking a line bundle on the spectral cover and, you know, pushing this forward to S. So PC here is the map from C to S. And so if we have a line bundle on C, we can push it forward to S, and that will give us a vector bundle on the surface S. We are really interested in SUN vector bundles, and so what the conditions that we'll have to satisfy is, first of all, C1 has to be an H11. So that's one of the conditions we discussed yesterday, and that's, you know, starting with this Hermitian-Yang-Mills theory, we get a condition from the BPF equations that F20 has to vanish. And furthermore, we would like to have an SUN bundle, so the C1 of P star L is equal to 0, so that's like a traceless condition. And the main idea how we construct line bundles on C is by pulling back curves from C, or in fact pulling back curves from S to C, and then constructing you know, these line bundles from the dual 1-1 forms. So I don't know whether I want to go through that. Actually, let me maybe just summarize here and then discuss the fluxes in the global model later on. Okay, so just to sort of maybe summarize what we've done so far. We started off with 8D Supergravity on S times R1, 3 with a Higgs bundle, which was giving us the gauge field and phi. The point I was trying to make today is there's a sort of very It's not the most general way you can study these things, but there is some important information encoded in the spectral cover. Is there a question? No? Okay. There's important information encoded in the spectral cover, which is just the eigenvalue data for this Higgs field. And for the context of SU5 gut model building, it was sort of the idea was we start with SU5, we get all the different kinds of, matter and Yukawas from higher rank enhancements. So one way we can sort of put a framework, of where all of these things can arise from Higgsing down a higher rank age group is starting with the E8, and then looking at an SU5 spectral cover for that. And C is really, the way we think about C is as a branch covering over the surface S. We can also construct the gauge component of this. What I like to sort of emphasize at the very end today is, or this hour, is that this was an example for an 8D super Young-Mills theory. The reason, as I said, will be clear in about half an hour when we say, okay, all this can come from some F-theoretic construction. The reason why I'm sort of starting from this gauge theoretic point of view, discussing the Higgs bundle, et cetera, is that this is really a framework that's not just limited to this 8D theory. You could, if you remember the heterotic string, the first couple of slides, yesterday we had a very similar kind of structure, actually. So in fact, if you look at a heterotic string in 10 dimensions on a Calabi-Yau that's elliptically fibered, you also have a spectral cover construction to describe matter Yukawas and also the vector bundle in that context. And in fact, sort of one direction I think that string phenomenology can sort of go into and I think be very systematic about these studies that was proposed by Martin Weinhold in a couple of papers is that you can also apply this actually to 90 super Young-Mills, like this will be type 1 prime type phenomenology, or 70 super Young-Mills, which will be M theory on G2. So the whole mechanism, right, this whole study of spectral cover, we look at the loci where symmetry enhances, and then constructing bundles over the spectral cover to get vector bundles. That whole story will carry over very generally. So that's why I think that's a systematic sort of approach that one can follow and make some progress without being too limiting. And that was sort of the main aim of, as I said yesterday, it's really the way I think one should approach string phenomenology. Anyway, so today we'll continue actually with sort of making it a little bit more precise where these Higgs bundles for 8-dimensional super Young-Mills come from in the context of string theory compactification, and that'll get us to what F theory is. So in the next lecture, which I think will be in half an hour, I will completely switch gears. And first of all, it won't be clear where all this will be fitting into, but I'll discuss, first of all, what F theory is, then study actually lots of geometry that will be relevant. And at the very end, we'll see how that connects back to these Higgs bundles. Okay? So are there questions?
So are there any questions for Puffy?
Sorry.
Sure.
Could you say something more about how you actually construct fluxes from that spectral cover?
Yeah.
That was a bit quick for me.
Yeah, well, I mean, I skipped it because I said I'll discuss it later, but we can discuss it now.
Then I can just wait, sorry.
Huh? No, we can, or you can come forward and I'll explain it to you.
I have a quick question.
Sure.
You were mentioning that Weinhold was saying you would apply these methods to G2.
Yes.
All these methods seem to rely heavily on having complex surfaces.
No, it doesn't, because in the G2 case, you then build a spectral cover over a 3 cycle, right? So then you had, indeed, the computational, tools, how you then compute zero mole, all that will change, but the whole structure of there'll be a Higgs bundle, how you construct vector bundles over that, all that carries over. So then you don't have a 4 cycle, but you have a 3 cycle. Sure, it won't be complex geometry, but then you'll have to study, in that case, that's something that Tony Pantev and Martin were doing, that you need to do Morse theory. So, you'll have to pick the way that you then describe the theory, but the whole setup is completely carries over. Yeah, you had a question.
Yeah, I think I missed the motivation for going all the way up to E8 unification.
Yeah.
Hours, you can stop at E7.
So you can start with E7, that's right. So you can start with E7 if you like. And you can also look at spectral cover starting with E7 and then going down. In fact, you could have started also here. The thing is, E8, so there's a nice story, in fact, it relates to, so there are two reasons. One reason is, you can, when you start with E8, you actually get some more, phenomenological, freedom. So you get additional singlet states, they could play the role of some right-hand neutrino, etc. That's sort of one reason. The more, I think, underlying reason is there's, for certain instances, when F theory, so this is coming from F theory, right? When F theory is dual to actually heterotic. So when you have, in F theory, a K3 fibered, so you have a K3 fibration over a surface S. Then there's a heterotic dual. And in the heterotic dual, the description in terms of spectral covers, right? It's actually a heterotic dual on an elliptically fibered Calabi-Yau threefold. There you have a spectral cover description that's, that's not by now classic literature for an E8 times E8 sort of, heterotic string. There, the structure is completely identical in that duality to the structure just described. So,
I suppose you're just worried about proton decay, for example. Can you address it at the level of E7? Or?
You're satisfied with the question you asked before?
No, it's the same question.
No, it's not the same question. Sorry. So you asked one question is why E8? Yes. And I explained to you why you go all the way up to E8, because then there's a real nice map to heterotic, and a lot of these data were carried over.
Aesthetical, but
and now you're asking about proton decay.
If you just are interested in doing model building,
yes.
I think you have answered the question.
So if you just want to do model building, in fact, I can tell you also, indeed, then it becomes related to this. So if I started with E7, there's no 3 plus, so then the cover would be smaller, right? So it would just be a 4-fold cover. You will not have a 3 times 2 cover. So all the covers that you will have with E7 will just be a subset of this, yes? And I know for a fact that you will not be able to get rid of the PQ type, so of the Q cubed L operators. I mean, you won't have a PQ type symmetry unless you have this 3-2 cover. So your models are probably not good.
Okay, well, let's have our coffee and come back.